So this lesson is on one-dimensional motion, both in the horizontal and vertical direction. The key thing I want you to make sure you get from the opening is that the gravity is negative 9.81 meters per second squared. On the AP test, however, you can round to 10, so that's good news for the AP test, but for the class, we'll definitely be using this number, so make sure you know it, and you know it well, so if you move on to AP Physics 2 or C later on in your career, you know what gravity is, and it's nothing different. So to make sure we're on the same page, I want to make sure we use these symbols moving forward. The only thing different is when I move to the Y direction, so again, I want to make sure we're comfortable with these symbols, and we use the same ones. In the Y direction, I'll change the X to a Y, but a lot of times I'll leave it because X represents position. So I probably won't change it, but there's a possibility I will. We have three main equations. In class, we have derived this middle equation. In getting there, we had to derive the first equation. The last equation, I will not derive in class, or I won't take the time in this video to do that. But the key point here is to remember that in the first equation, that position is missing from it. So if I don't know position, but I'm looking for one of the other variables, I could use it. Same thing with the second, missing the final velocity and the missing time. So those are key points in the information, because I will not have all the variables given to me in the problem, but yet I can still use these equations to find the missing one that I'm looking for. Again, just kind of following through the process of solving a physics problem. We draw it, we list all of our variables, all of our knowns and unknowns. We determine our frame of reference, so basically where am I standing to visualize this problem when I draw it. I add my knowns and unknowns to my picture, so that way I know what I'm looking at and what I'm looking for. I can get a very clear mental picture of what's going on. Using my list, I pick the appropriate equation and then I solve for the missing variable. So let's do a rundown, real quick practice in the horizontal direction, and then we'll look at the vertical and some of its uniqueness as we move forward. But in the horizontal, it's pretty straightforward, right? How long would it take a car starting from rest and accelerating uniformly in a straight line at 7 meters per second squared to cover a distance of 350 meters? All right, so I'm looking for time. I know I want to cover a distance of 350 meters, so I'm going to set the initial position to 0 and make my final position to 350 meters, just to save me a little bit of math. Set it starting from rest, so I know that my initial velocity is 0 meters per second. And it gave me the acceleration of 7 meters per second squared. Now I'm going to choose not to draw out this picture because the car is accelerating in a horizontal direction down a road, so it's pretty easy to mentally conceive, and so I'm just going to kind of ignore it and just move forward because I'm really looking for time. Now, I don't have my final position and I need time, so I'm going to use this equation based on my list to solve, and so I'm going to do that for you now. So there's my answer. 10 seconds is what it would take for a car to accelerate 7 meters per second squared to travel 350 meters. All right, so let's look at vertical. Some really uniqueness to vertical. When I draw the object going straight up and straight down, I have to draw it in kind of this arc shape because it's really hard to see a ball flowing straight up and straight down in all of its paths that it takes place. So I'll kind of give you an example here. Change the colors of a line. All right, so if I had, let's actually change that to an arrow. Okay, so if I threw a ball straight up, in which it came straight back down, because what goes up must come down. You get something like this. Now, they're not perfectly overlaying each other, but it's really hard to see what's going on. So you get the idea. So because time is continuous and time moves on, I actually use this kind of arc shape that you see to the left of those two arrows to kind of see exactly what's going on at the top and bottom and how the ball's moving in a graph sense. But in two-dimensional shape, I'll always, in class, always draw it as an arc so that way I can see up and down. I won't draw it on top of each other. Okay. Again, just like I said at the very beginning, gravity, the acceleration due to gravity is negative 9.81 meters per second squared. In your book, they'll use the symbol G for gravity. I will use A because I know the acceleration is not changeable in the y direction is negative 9.8, and because that way I don't have to memorize a new equation using this new variable G. So I just know that in the y direction, the acceleration is going to be negative 9.81 meters per second squared. And that's how I will do all the practice problems during class. So just know that in your book, they use the letter G. I will use the letter A, but I know that it's in the y direction, so therefore it's negative 9.81. Some people can't keep that straight, so they add another letter, but that just changes all the equations, and I choose not to do that and just remember that in the y direction, the acceleration is negative 9.81 meters per second squared. Now, the uniqueness of this is that you'll see when we get to the class is that at the maximum height, velocity will be 0, so the ball will actually freeze for a split moment, just for a moment, and then it will continue back down its path. So at the very top, my velocity is 0, so therefore my final velocity in the uppermost portion, y final, would be 0 in the up direction, but in the downward direction, the initial would be 0. So again, we're going to divide these in up and down. All right, if I have both up and I have both down, if I have the full arc, I'm going to divide it in half and work as them independently. All right. Now, quick little side note here to see is that if I start from the same height and land at the same height, all right, my initial velocity is equal and opposite to my final velocity. So that's a good thing to remember because we won't always get the final velocity. All right, so let's look at an example. A brick is dropped from a height of 9.5 meters. The brick will impact the ground in approximately how many seconds? So again, I'm looking for time. So what do I know? The brick is dropped off of a height. So my initial position here is going to be 9.5 meters in the air. So the final position is 0. So let's see if that makes sense. So if I have, say, a building or a cliff, let's say a cliff, and I have my little brick. Well, it says that it's dropped from a height of 9.5 meters. So that makes a lot more sense that I'm setting up my initial and my final the way that I am. Now, it says dropped, it's not thrown, so therefore I can assume my initial velocity is 0. I do not know my final velocity, and I know that my acceleration due to gravity is negative 9.81 meters per second squared. Now, you notice I added the 3 equations that we used in the x direction, but they're all written as if they're in the x direction. Again, x and y are separate, but instead of having to memorize the same equations but with the little y down here instead of an x, I choose to memorize the initial equations without the x and y's, and so that I can just move forward and just add the x and y and keep them separate. So it just saves me some memorization of what we're going to do. All right. And so based on my equation, or my list over here, I am going to choose to use this equation again. But again, I want to use all the information I have over here in my list. So let's do that now. So with significant figures, my time that it would take for my brick to fall would be 1.4 seconds. Because I only need 2 significant figures. So my time would be 1.4 seconds with significant figures. So I apologize for my pen messing up. And good luck.